Hello friends, welcome back to my YouTube channel MS Maths. In this video, we are going to discuss about the theorems and example related to measurable function. So what is a measurable function? The concept we have discussed in our previous video. So first of all, watch that video from the playlist of the measurable set, the channel. And if you like the video, then please share the video, subscribe the channel and like the video and watch till the end that you can get the concept, the whole concept, or your time will not be wasted. So basically, we'll discuss one by one two example. So first we'll discuss if we have f and g be two real valued measurable function, then with domain E is the domain, and c be any constant, then prove that f plus c, f into c, f plus g, f minus z, and f into g be a measurable. So we'll prove all these measurable one by one. So how can we start with this? So let's start the topic and start the solution. So first of all, we'll take just example of just example of f plus c. So f plus c be measurable. So if it is measurable, we want to prove is measurable or to show basically. So what measurable function is what x such that basically measurable function is basically the x such that f of x is greater than alpha for every alpha belongs to real number. Then we have the function f of x is what f plus c. It means x such that f of x plus c greater than alpha for every alpha belongs to real number. So I can write it just as alpha f of x greater than alpha minus c for every alpha minus c belongs to real number, and also the alpha belongs to real number and alpha minus c is also belonging from real number. So I just write it is what greater than capital alpha is basically the for every capital alpha belonging from the real number where capital alpha is alpha minus c. This is what the measurable function. So it is the measurable function and it is just equivalent to f of x plus c. Now, next, second. If we, second one is, I think, second one is f into c. Yes. So the second one is f into c. To show that c into f of x is measurable function. So what here c be any constant, then let c greater than 0. So the case number 1, c greater than 0, case A. So x such that f of x is greater than alpha is what? X such that f of x is greater than alpha upon c. If c is greater than 0, or basically we can say c is not 0, or basically we can just write it is what? C into f. Okay, c into f of x can be written in such a way. So it can be written in such a way that for every alpha belongs to real number, and obviously if c is a constant, then alpha by c is also belonging from this. Then it is a measurable set. Similarly, when c is less than 0, then what? X such that c into f of x is greater than alpha is what? X such that f of x less than alpha by c. Then by the property, see what are the properties that we have already proved in the previous video is basically the 4 property we have. F of x such that f of x greater than alpha. Second one is f of x greater than equal alpha. Third one is f of x less than alpha. And fourth one is f of x less than equal alpha. For every alpha belonging from real, all four properties are equivalent. If all four properties are equivalent, then this property is equivalent to f of x greater than alpha by c. Then this is a measurable. So to be a function, to be a measurable set, should we follow these all properties? Okay, next. Next one is f plus g. If these both are measurable function, then we'll just add both these. So if f and g both are measurable function, then we can write what? F of x such that x greater than f greater than alpha for every alpha belongs to R, and g of x is basically x such that g greater than some beta for every beta belonging from the real number. Yes. Now let x such that f plus g less than alpha, then we can write x such that f less than alpha minus some g. Now let R of I is rational such that f of x is less than some R of I. It means it is less than alpha minus g of x, such that, okay, in such a way that R of I there exists. It means what? X such that f of x less than alpha minus g is basically the union of I is x such that f of x less than R of I. Intersection what? X such that g less than alpha minus R of I. Now you can see, if I will just write f, then it will be R of I. If I will write g, then what? I will take this part and my g is less than, you can write this as g is less than alpha minus R of I. It means these both properties are equivalent. And now the intersection of two measurable set. It is measurable set. It is a measurable set, and it is what? A measurable set or measurable function, you can say. This is what it's measurable set. Then now the intersection of measurable set is also measurable. Then f plus g is measurable. It means this is like this right hand side is also measurable. So this will also be measurable. So if it is a measurable function set, then this is what? Measurable function. F plus g is a measurable. And now I think last one is the f minus g. Similarly, we'll put f minus z and f into g. Okay, we have two more f minus z. So next one be the, I think, fourth one. F minus of g is measurable. That's what we want to show. Okay, f and g both are measurable function, and by the previous result G into F is also be a measurable function. Then F plus C into Z is also be a measurable set, or sorry, measurable function. Also be a measurable function if, sorry, because sum of two measurable function is also a measurable function. Then if C is equals to -1, then F minus Z is also be a measurable function. Okay, that's this we have, and this thing we have. We'll just put C is equals to -1, so it will be F minus G. Now the fifth property is what? To show F into G, no? F into G. To show F into G, or basically F, yeah. To show that F square is measurable. To show that F square is measurable. It means the multiplication of two measurable set. That's what we will just replace F with the G. Okay. If X such that F square of X less than or greater than alpha, because all these are equivalent, so no worries. So it will be just X such that F less than root of alpha, or basically union of X such that F less than minus of root of alpha. So it is what? The union of two measurable set is measurable. Okay, this is what the union when alpha is greater than equals to 0. For every alpha belonging to this, then F square is measurable. So if we just replace 4 of Fg, that we can write what? 4 of Fg we can write just F plus G whole square minus F minus Z whole square. It will be measurable. It means F of G can be written as 1 by 4 F plus Z whole square, and F minus Z whole square is measurable. This is the technique that we have proved. This is the measurable. It means F is measurable, this is measurable, then addition of the measurable function is also measurable. Same, the addition of measurable function is also measurable. Then the square of the measurable function, if it is a measurable function, then the square of the measurable function will also measurable. If these both are the measurable function, then it will be equals to some 4 g of x, or basically 1 by 4 of these both. The difference divided by the 4 is this basically the multiplication of f into z. It is what? Measurable function. This is the technique to prove these all results. Okay, now let's start with the some another result, or with some another example. Sorry. Let Fn be a sequence of measurable function defined on same domain, then prove that supremum of f1, f2, f3, fn is measurable. Infimum of f1, f2, f3, fn is measurable. Limit superior of fn is also measurable, and limit inferior is also with a measurable set. So let's start with this. So we'll start the first one. What? Supremum of f1, f2, and so on, fn is measurable. How can we start? I just take h as my function, basically that is supremum. So just let h of x is what the supremum of f1, f2 and so on fn, means x such that h of x is greater than alpha is basically the union I is equals to 1 to n x such that fi of x greater than alpha. Okay, it means this can be written if it is a function or it is a miserable. If we want to show that it is a miserable function, then we can write it is in this way. So now by miserability of function f of I, basically I less than n, where n belonging from the natural number. Okay, so for each the set x such that f of x greater than alpha is basically the definition of the miserable function is also miserable for each I and alpha belonging from real number. It means the union I is equals to 1 to n is what xi, fi of x greater than alpha is also miserable set. Then if it is a miserable set and it is what it is equals to this, then x, basically h of x is greater than alpha is miserable, and this is what the supremum of fi is a miserable set. Okay, so this is the technique. We'll just put it as a function and we'll just replace it as yes, where I is greater than equal 1 to I is where I varying from 1 to n. Okay, yeah. Next, so we'll take just one function as to show that the limits or basically the infimum of fi is miserable. Okay, so let us taking g of x is what the infimum of f1, f2 and fn. So x such that g of x greater than alpha is equals to the intersection I is equals to 1 to n is such that fi of x greater than alpha. For f of I is varying from 1 to n, then the set intersection, or basically you can write just the set intersection I is equals to 1 to n x f of ix greater than alpha is miserable. If it is a miserable, then the set of gx is basically x such that g of x is greater than alpha for every alpha belonging from the real number is also be a miserable set. It means the infimum of f of I is also miserable. Now next, the third one is the limit superior. So the limit superior of f of I is basically what the limit supremum of fn is what the infimum of all supremum from I varying from 1 to n is basically n, or basically what, wait, if it is fn, sequence is what the fn is the sequence, then infimum of all supremum greater than n, where k greater than n is what? Fn plus 1 up to Fn plus k, or Fk, sorry, Fk. So it will be what? The infimum of n. You can write just infimum, and it is what? The supremum of Fn plus 1 up to Fn, or sorry, up to Fk is a since supremum of Fn and infimum of Fn both are measurable according to the result 1 and 2, then the infimum of supremum of Fn is a measurable set. Similarly, fourth, what is the limit inferior? Limit inferior of Fn is what? Limit infimum of Fn is basically the supremum of all infimum of function Fk, where k is greater than n. Similarly, you can do the same. So this is what the concept of the measurable function and the example and related theorem. So thanks for watching my video. Keep watching MH Maths. For more video, you can subscribe the channel. You can visit the channel for higher studies or higher mathematics. Thanks for watching my video. Keep watching MH Maths. Thank you.